So number 4 says 5 and then the square root of 24 times 2 and the square root of 28. So you could choose to multiply 24 and 28 together first, or you could break those two numbers apart and multiply last. So Tyler, what did you do first?
I broke them down.
Okay, so if you look at 24, how did you break 24 down?
I did the square root of 6 and the square root of 4.
Okay, and then 28 would be broken down as?
Square root of 4 and square root of 7.
And then we still have a 2, and there's still a 5. So that would be like the numbers broken down. Once you take the number out of the square root, the square root of 4 is 2, then you're multiplying this 2 and that 5 together. So that I have now 10 square roots of 6. That's what 5 square roots of 24 reduces to. And then there's a multiplication symbol. And over here, the square root of 4 becomes 2, so then you're multiplying 2 times 2, so that's 4, and it's still the square root of 7. But then what do you have to do yet? Because it's not quite done yet. Tyler? So then you still have to continue to multiply. So 10 times 4, Tyler, is 40. And 6 times 7 is 42. And then the last question you have to ask yourself is, can there be a value that goes into 42 yet as a perfect square? So does 4 go into it? 9, 16. Does 16 go into 42? So then you would be simplified. Whereas if you multiplied first, you would take 5 times 2 and get 10. Take the square root of 28 and the square root of 24 and multiply those together. So you could multiply first and then just break it down immediately. And it saves in like all of the extra multiplication that you're doing. Right.
That was my question. I like that it doesn't matter.
Please pardon the interruption. For the following students, please report to A218. Adam Worsing, Noah Maxwell, Cedric Raymond, Andrew Longjohn, Joey Pastoris, Kevin Lavasic, Alvin Lagoon, Wade Tafwheat. Thank you.
Is there another question from the practice worksheet that you'd like to go over? Keith, I saw your index.
36.
36. So 36, for a period of 48 months, the average monthly operating cost for a small business can be modeled with the equation C equals 0.55 t squared plus 55, or 550. T is the number of months. It says, during which month was the average operating cost $1,430? So how would you approach that problem? What would you need to do first? So the cost to run this company is 0.55 times t squared, which represents the number of months, plus 550. And this equation is good for 48 months. So anything beyond 48 months, there would be a different equation. But you're actually not using 48 months in the problem. So what would you be plugging into the problem then, Tyler?
The 1,430.
Yeah, and that's the cost to operate the company. So 1430, and then 0.55 t squared plus 550. So to solve this, Anastasia, what would you do first to solve it? Yeah, subtract 550. Anastasia, do you know what 1430 minus 550 is? 880. And then Anastasia, what would you do next? Is that what? Okay, so this was 11/20, so she multiplied by 20 over 11. You could have also just said, hey, I just want to divide by 0.55. That would have been okay as well. What did you get, Anastasia? So it actually worked out kind of nice. And then the last thing, take the square root, because we have a t squared. To solve for t, we have to take the square root of it. And Anastasia, you got 40. Because the square root of 16 is 4, So the square root of 1600 would be 40. So that would be 40 months. But it asked you during which month was the average operating cost 1,430. So how would you decide which month that represents?
Would you divide by 12 and then find what part of the year it is?
Yeah, so divide it by 12. So if you divide that by 12, it's what?
3 4/12.
So 3 years and
4 months.
4 months. So which is the fourth month then, Greg?
April.
So 40 months is really 3 years, which is 36 months, and an extra 4 months. So the month would be April because it's the fourth month in that third year. Questions with that? So plug in the number, the 48 is just saying that this equation is only good for 48 months. And then you get the 40 months, but then convert that to the fact that that's really 3 years, 4 months, the fourth month is April. Any other questions from the worksheet? 19. Alright, so 2x squared plus 5x equals 5x squared minus 37. Need help? Sure. So Tyler, W in the back, how would you start solving this? What'd you do?
I took the 5x squared to the other side.
Okay, so subtract 5x squared. What else would we move then?
The meter, or the 5.
Yeah, so subtract the 5x squared, so that gives us negative 3x squared. But then also get the 5 to the other side. So Tyler, negative 37 and negative 5 is? Negative 42. And it doesn't matter which side you take the number and the variable to. So I'm a person who always likes to have my variable on the left and the number on the right, but maybe you like to have your variable be positive. So maybe you move the 2x squared to the left and the 37 to the right. Totally up to you. So Tyler, then after that, what do you do next?
You divide by
What is negative 42 divided by negative 3? 14. So take the square root. Anytime you take a square root, Tyler, what do we need with all of the problems? Unless it's a word problem.
See if it's perfect square.
To see if it's a perfect square, but what else goes in front of the square root?
Plus or minus.
A plus or a minus. The only time you don't need that would be if it's a word problem, or if you're not really solving an equation. So we need that plus or minus. Is there a perfect square that goes into 14? No, there isn't. So x equals plus or minus, and then the square root of 14. But if you're solving an equation, every equation that we solve from now on has that plus or minus with it every single time because it's a parabola that takes account for the negative and the positive side of the parabola. Questions on that one? How about from the book homework? Were there questions that you ran into as you were doing the book homework? So then if you please make sure your name is on your homework, at least the front page that we stapled, and you can pass that forward.
Me and Grant, I don't know if anyone else turned it in yesterday, so I don't know.
Yeah, I have some from yesterday. Yeah. Did you turn yours in yesterday?
Yeah.
Who's strong?
Yeah.
That's not easy.
And Grant, you turned yours in yesterday. So we're going to talk about imaginary numbers today. Yeah.
No.
And I think you'll see that the concept of an imaginary number might be a little different, but actually working with them is kind of like working with a variable. So it really isn't any different than looking at it as an x, it's just an imaginary number instead of an x. But the reason we work with imaginary numbers is because sometimes you're going to have negatives underneath the square root, and they actually do make solutions to problems. And once we start investigating larger powers, you'll see that they are part of equations. So we want to make sure that we're finding all of the pieces of the equation. I believe it's page 27 in your packet. So on page 27, it talks about the imaginary unit I. And why do we have the imaginary number I? So how do you get the imaginary number? Justin? So the square root of a -1, when you put it in your calculator, the calculator says error because the calculator isn't functioned to deal with negative numbers. But instead of saying you can't do the square root of a negative number, you can't calculate it, math people try and create things so that essentially everything will work so that you can continue on with every problem. Just like factoring. If you can't factor it, all right, well, how else can we solve the problem? That's why other methods are created to solve quadratics besides just factoring. So when there's an imaginary number, a -1 underneath the square root, that really makes the I. But the part that makes the I is the negative part. So really you're pulling the negative outside, but then you're still keeping the square root of the positive number. We generally don't write +1 underneath the square root because we know that just equals the value of 1. But the negative part underneath gets moved out, and that's the part that becomes the imaginary number I. But then you still have the square root of the positive number left. So if we had the square root of -3, that would really be equal to what?
I the square root of 3.
Right, it would really be I because that's the negative part, and then the square root of 3. So the negative underneath the square root, you can't take the square root of a negative number when you plug it in the calculator, but that's the part that creates the imaginary number. So there's two other parts underneath here. A complex number is when you have a real number and an imaginary number in an expression. And there's a way we write complex numbers. So you're going to have A, which is the real part, plus BI, that's the imaginary part. So the real number gets written first because it's the real number. It's more important than the imaginary number. You write the imaginary number second. So just like all of the answers to our problems with square roots, the whole number gets written first, the square root number gets written second. So numbers do have orders that you put them in when you're writing solutions. So A plus BI would be a complex number because it's a real number and an imaginary number in the same expression. An imaginary number is anything with an I in it. So any number with an I or any number when you're taking the square root of a negative number. So I'll say any square root of a negative number. So if we had the square root of -9, what would that be? What's the square root of -9? Michael? So you're so close. So it would be I in the square root of 9. But what is the square root of 9? 3. So you take the square root of 9, it becomes 3. And then we would put the I with it. So the negative part makes the I, but then you can still take the square root of 9. and then it becomes the 3. So it would be 3i. So the square root of negative 9 is really 3i. So you're still allowed to take the square root, you just have to have an I with the answer. So I believe underneath there are a couple properties of imaginary numbers, maybe. There we go. So here it says if r is a positive real number, then the square root of negative r is really the imaginary number times the square root of the positive value left underneath. R just means any real number that's left underneath there after you take the negative out. So here's this example which we kind of already talked about. The square root of negative 3 is really I, and then the square root of positive 3. Before we get to the second property, so if I have the square root of negative 1, we know that makes I. What do you think I squared would be equal to?
Negative
Why negative 1?
1. Guys, you're taking away the square root of 3, so
Yeah. So if I is equal to the square root of negative 1, if you square both of them to get I squared, you're taking away that negative, or the square root symbol. So I squared is negative 1 because of that fact that you're really just squaring both sides. So if you look at property 2, it says by property 1, it follows that I times the square root of r is equal to negative r. So that means if I have I times the square root of 3 squared, you would have I squared and the square root of 3 squared. That's what that really means. You're squaring both pieces. So, Ethan, what is I squared? Negative 1. And then the square root of 3 squared is just 3. So really that makes negative 3. So if you're squaring a whole quantity, you're squaring the imaginary part, so that makes it I squared. You're squaring the square root of 3 part, well the square root of 3 is 3. So I squared is negative 1, so that's how we get that negative 3. So that's going to be a property that you're going to kind of think about and remember. So when you have an I, you have an I because it's equal to the square root of negative 1. But we'll also have I squared, and that's just equal to negative 1. Because if I square the square root, then that square root cancels out. And you could find that for any power of I. So we could work like with I to the 4th, I to the 5th, I to the 6th. They all just kind of build on itself. So you use the previous properties to get the next power. Alright, so if you look at example 1, we're going to solve these quadratic equations, kind of similar to the quadratic equations that you worked with the last 2 days. We have 2x squared plus 15 equals negative 35. So Grant, how would you try and solve that equation?
So first I would subtract 15, so that would be 2x squared equals negative 50.
Okay.
Then I would divide by 2, so it would be x squared equals negative 25.
So we've got x squared equals negative 25. And then to get x by itself,
And yeah, you have to get x by itself, so you have to square root these. So you're left with x equals the square root of negative 25. And then that simplifies to I times the square root of 25. And that simplifies to 5i.
good. So then that's 5i. So there's one thing that he's missing. Everything is perfect. I've got a great explanation.
Plus and minus.
One piece that he's missing is the plus or minus. So anytime you solve an equation and you get rid of x squared by taking the square root of both sides, we need to put a plus or a minus in front of that square root. So there's still two answers here because it's still a parabola. We still have the left and the right side of the parabola. So it's plus or minus and then 5i. So you guys don't need to show this step right here. So you can automatically go from the square root of negative 25 and say that's plus or minus 5i. So you don't have to show the step where you're pulling out the I and then taking the square root of the number. So if you look at the one next to it, we have 3x squared plus 13 equals 23. So you would take the 13 to the other side, and then divide by 3. So now we have x squared equals 10/3. Emerson, what would you do next then?
You would, I guess you just square it out.
Yeah, square root both sides. So I'm going to throw that plus or minus in front. And now we have the square root of 10/3. We've got the square root of a fraction. It's not imaginary, so we don't have to put an I in it, but we have a square root of a fraction. Emerson, do you remember how we can simplify the square root of a fraction?
There's a square root over each one.
There's a square root over each one individually. And then what do you have to do with that, Emerson?
And then you multiply times the square root of 3 and the square root.
Right, so we talked about rationalizing the denominator. So we don't keep a fraction underneath an entire square root. Instead, you think of it as the square root of the top and the square root of the bottom. But you can't have a square root in the denominator. So you have to rationalize it by multiplying it by itself. So Emerson, the square root of 3 times the square root of 3 just becomes 3. And then on the top of it, we end up with the square root of
-3.
10 times 3? 30. Did you say 30 and I just didn't hear you? I'm sorry. Can you break down 30 at all? No. So we have plus or minus the square root of 30 divided by 3. Remember, don't divide these. They stay like they are. So it doesn't simplify any further because you have a radical versus a real number. And they don't mix together. You can't divide. Questions? So solving an equation with an I versus solving that equation without an I. You still solve it the same way. It's just you pull out the I for the imaginary part because we had a negative underneath. All right, so the other thing that we're going to do with these is just some basic operations. So we can add, subtract, multiply numbers with I. And you'll see that it kind of follows with like terms. So when you're adding x's, you only add x's together. If you're adding y's, you only add y's together. And that's the same thing with complex numbers. So to add or subtract two complex numbers, you have to add their real parts. So essentially, if it's a real number, it gets added to another real number. And then their imaginary parts separately. So the real gets attached with the real, the imaginary gets attached with the imaginary. They never combine together.
Say if there's an unsimplified radical, those would be separate as well. Okay.
Yes. Yep. So it's showing you here if I take A plus BI, C plus DI. My husband isn't dying, so that's good. He just wants Jell-O. Important things to want. Jell-O. Pick Jell-O up before you come home. So you're adding the real, the A and the B here are the real, and then you're adding the BI, the DI, those are the imaginary parts. So really you're just thinking about adding those pieces together. So if you look at the two examples underneath, we have 6 plus 3i minus, and then the quantity 4 minus I, and that's an I back there, that second one. You don't have to think of it like this, but this is kind of like what the thought process should be, but you don't need to really separate it essentially like this. But what you're doing is you're taking the 6 and the 4, and now it's a negative 4 because this negative distributes through. You're combining those two pieces together because that's the real part. So we would have 6 minus 4. So that's my real value. And then the imaginary number, we have a 3i, which the I is pulled out, so really you're taking 3, and then minus a negative I would be plus a positive 1. But when I work through this, like I'm just thinking that I'm taking 6 minus 4 and then 3i plus another I. Like, I don't think you really need to like group and pull the negative out. Think of it as an x, you're adding like terms. So 6 minus 4 is 2, and then 3i minus a negative I makes a positive 4i. So if you don't want to follow the little notation that they have underneath, that's fine. Just treat it like a like term. So what pieces get added together? So you're kind of just looking at like terms. So we have 2 plus 5i, 7 minus 2i. Well, the 2 and the 7 are the like terms. And then the 5 and the negative 2i, the 5i and the negative 2i are the like terms. So Jesse, if we combine our like terms together, what do you get? So 9 plus 3i. Writing it in standard form just means the real should be first, the imaginary should be second. But like actually separating it and showing that you're grouping the real numbers together, that's not necessary because if you just think of it as like terms, add the reals, combine the imaginary numbers, I think it makes it a lot easier to think about it that way. Questions? So the other set of problems would be to try and multiply. So it says multiply the complex number and then write it in standard form. How do you think you'd go about multiplying these? Grant? Yeah, you're going to FOIL it. Just like it was an x, you FOIL if it's an x, we're going to FOIL it if it's a complex number. So the first two terms, so Grant, 2 times negative 5 is? Negative 10. So we're FOILing it just like you would FOIL values with x, binomials with x. And then Grant, 2 times 2i would be? 4i. The middle terms, I and negative 5. Negative 5i. And then your last terms, we have I and 2i. Plus 2i squared. So if it was x times x, we'd make it x squared. So now it's I times I, so you're making it I squared. So that would be the FOILing part. Now we need to combine some things together here. So Megan, what would we combine together? So 4i and negative 5i, what's that make, Megan? A negative I. And then if you go back to the part here, we have 2i squared. Is there anything we can change with 2i squared? Do you know, Megan? So we can make an I squared a negative 1. So I squared is equal to negative 1. Because when you square both sides, so if I started with my I squared equaling negative 1, the square root of negative 1, if I square both sides, I squared is equal to negative 1. So I can change this to be a negative 1. So then when we're trying to simplify it, we have a negative 10, and then 2 times negative 1. So Megan, what's our final answer going to be? And then minus I. Nice job. So FOIL it like you FOIL an x, and then start simplifying it. So combine your i's together, and then I squared is going to be in the problem, but I squared is really negative 1. So now I have 2 times negative 1, which makes negative 2, and then my negative 10 is negative 12. So I believe there are 3 problems at the bottom. See if you can combine like terms, add the 2 expressions, maybe multiply, like letter B is multiplying. Get those problems simplified. So Kirsten, what did you get for letter A?
I got -4 minus 9.
Good, so make sure that you're distributing the negative through. So she said -4, and then what was your next one?
minus I.
Minus I. So this really makes a -16 minus 3I, so when you're combining those like terms, you get -4 minus I. So letter B, we have -4I and then times 9 plus 5I. So great, what would you do with that one?
Also, you first distribute the -4, so that would be -36I minus 20 I squared.
Okay. And then,
So I squared equals -1, so you plug -1 in, so it ended up being positive 20 minus 36I.
awesome, so positive 20, the real number goes first, and then minus
And
36I.
would you factor out the front of it or no? Okay.
Keep it like that. The last one, Elena, what'd you get for the last one, letter C? Yes, you.
The final answer,
Yep, final answer.
-2 plus 7I.
Good. So she said -2 and then 7I when you combine the i's together. So like terms, getting the reals together, getting the imaginary numbers. -2 is first, it's the real number, and then plus 7I. Are there any questions?
Wait, what does this like do? Because like, why